this is another one of those days where I'll talk a little bit about the very specific analytic description of moduli space of pseudoholomorphic curves. That's going to essentially finish the discussion of geometric regularization. I'm probably going to come back to that and sort of philosophically review the transversality part of that. But then I want to get a little bit into abstract regularization and first say why can't we just always work geometrically, and then talk a little bit about what you do when you have a local Fredholm description, and that will get us to sort of the one thing I'm going to say about gluing in non-transverse situations, and then I'm going to forget about that because it's just technically sort of the convex span of different difficulties that we can deal with separately. So, quick review of where we were with the geometric regularization. Right, so there's also the sort of overall process is that you start with, in fact, a global description as a Fredholm section of this sort of space of pseudoholomorphic maps. In our case, for the Hamiltonian Floer example, there's an H perturbation on it, so we're looking at pseudoholomorphic cylinders. We're hopefully finding a J so that the d-bar operator, the perturbed d-bar operator, is a transverse section of this Banach manifold of maps. And if that is, then it's also a Fredholm section of a certain index, and so we expect the zero set to be a smooth submanifold of this larger set. Smooth. It's locally fixed index, so different connected components can have different dimension here. But that's not actually the space that we want to look at. We want a quotient by R shifts. So we observe and check, hopefully, that this finite dimensional submanifold of smooth cylinders has a free R action. Better check that it's smooth, and there's a properness assumption that then guarantees that the quotient still gets the differential structure of a smooth manifold. So that's the one that I want to sort of write as union of different actual manifolds of fixed dimension. And then we forget about all the higher dimensional things because we just want to get a homology theory out of this. And to prove that d squared is equal to 0, we need to go into identifying the broken trajectories with the products of zero-dimensional things with fancy way. Writing this as a fiber product over the periodic orbits is a fancy way of saying it's a finite union of pairs of moduli spaces where the intermediate orbit fits. So, oops. Drawing on this. Okay. So, to do this, right, we need to look at the uncompactified one-dimensional moduli space, and we're making this gluing map from pairs of from isolated broken trajectories times the gluing parameter into here. And what I argued at length is that that's well defined and continuous and injective for large enough R1. And the thing that I sort of hand-waved was a local surjectivity. So this is what we're going to want to prove, is that if I have some point in M1 that's sufficiently close to the broken one, then it actually lies in the image of the gluing map. And I can phrase this in terms of a sequence. Or I could phrase it in terms of an epsilon with a distance function. So here's some, the Gromov convergence here I'll spell out later on. Right? That really is sort of convergence of the shifts to this broken thing. So once we have that, well, and we also know that we can compactify M1 by just adding the broken things, right? So assuming there's no bubbling, right? Then that tells me that if I glue to this quotient space now this sort of compactified, broken trajectories times interval where I've added infinity. So I'm imagining infinity as not as the actual broken ones. I'm not gluing. Right? And then on the open interval, I glue this via the rho. Right? So then, well, that's a one manifold. That's a one manifold with boundary here, and I should. Right. The one thing, I guess I haven't checked. Well, right. We don't actually need to check. So rho, the claim is continuous. And this is going to say it's a local homeomorphism. So that gives this the structure of a C01 manifold. And all such things also have a differentiable structure. So, all right, I don't really care whether it's smooth or just C0 here. So I want a one manifold, because I want to know what its boundary is. So that's the story that then gives you d squared equal to 0, and then the sad thing is that you now have to, right, now you have a homology for some choice of j, and then for different choices of j you have to sort of run through this whole argument twice more to prove that the chain complexes are sort of sufficiently similar or that there's a chain map between them that then, and there's a chain map back, and that the composition then is chain homotopy equivalent to the identity. So you get an isomorphism between the homologies. So this part here is very nicely explained in the Salomon-Floer lecture notes. I mean, just the algebra and how the algebra comes from different kinds of moduli spaces. Right. And again, well, you could make the experiment whether once you understand this story, you can do all the analysis yourself. But it's sort of twice the same story again. So, right. But local surjectivity you haven't seen, and so let me try to actually properly do that. So let's see. So first of all, what is this convergence here? So that's, I guess, by definition. I'm going to pick one definition here. That means that some shift of the ui's converges to u minus, and some shift converges to u plus. And I'm just going to pick the representatives here, so that that's a symmetric shift. So there's a minus si and a plus si. And I want this with all derivatives on all compact sets. And the shift parameter should go to infinity. So that means I'm certainly capturing different parts of the energy of my trajectories, and then I want to make sure that I've actually captured all the energy. So the sum of the two limit energies should be my energy along my sequence. And I'm just going to fix that energy. I'm going to assume that that's constant along the sequence. One can always assure that the possible energies are actually discrete. So yeah, when you do converge to a broken one, energies will actually be constant. So that's what we have. And what we want, well, we want somewhere far down my sequence, I want to be in the image of the glowing map. And I have a uniqueness statement from the Newton iteration. Which says that if I have a holomorphic curve of the form U minus pre-glued with U plus of some zeta, and that zeta lies in the chosen complement of the kernel. So there was some dual operator, and it's small enough. So maybe there's an Ri here. So, and if my zeta in a W, we did Newton iteration with a W1p. So if that's smaller, then there's some uniform constant delta. Then I only find a unique solution zeta. So given this preglued thing, I find a unique solution zeta. And so that means if I can, and that is then in fact, this is rho of U minus U plus R. So what I do want to make sure is that I can write Ui as exponent of something that is small and lies in this given complement. And for that purpose, there's something I can play with, is I can shift the Ui another little bit. Epsilon can be large or small, or positive or negative here. So, silly, right? So if I can write U epsilon as rho, if I can write a shift of Ui as rho, then of course that's right. I'm lying here a little, right? So this rho here is a map, right? That's defined by taking the equivalence class here. But we defined a gluing map in a special parameterization, right? So where we work with the U minus and the U plus. So right, I want to exhibit a shift of the Ui as exactly the thing that I'm doing to get my gluing map. I guess, right, right, the uniqueness here, the uniqueness comes from also knowing that d bar of the Ui is 0. Right, so that's part of that Newton iteration. So it says there's a unique solution that's holomorphic and satisfies these conditions, but we know that our UIs are holomorphic, so, right, so that's the big piece of extra information. We know the UIs are holomorphic, and so now we just need to achieve a little bit of extra things. We need to keep that small, and we need to get ourselves into that complement. So let's see how we do that. So first of all, I'm going to sort of capture almost all of the energy in some fixed intervals here. So I'm going to say that this is, I'm going to pick a k pretty large so that almost all the u minus energy is on this interval of minus k to k, and also almost all the u plus energy. So then I also know that these intervals of u minus and u plus are very close to the shifted intervals for the ui's. So this sum here is approximately equal to the energy of ui as I shift appropriately. So that's the shift that comes from the u minus here, and then the shift from the u plus is from k, goodness, no, also minus k, right, plus si to k. No, wait, minus, oh geez. Oh, both plus si, right, right. I just have an interval of width 2k, and I'm shifting it minus si or plus si. Right, so in particular, probably my shifts are going to be much bigger than k, so that these are actually two non-intersecting intervals. So, and so this is approximately equal to that, is approximately equal to that. However, that is also the full energy of ui. So that means there can't be a whole lot of energy on the complement of these intervals here. So, particularly, so this is bigger or equal to this fixed energy minus some small quantity epsilon k. I know that that goes to 0 as k goes to infinity. So that's going to control the energy on the complement.
So is this k just coming from some assumption, just like exponential decay at the ends? Is that?
Well, it comes from, well, yeah, that's the question, right? This energy is an improper integral from minus infinity to infinity. Right? And so even just saying that the energy is finite says that this, as k goes to infinity, converges there. So, and of course, so when I write e of ui, that's, it has to be a finite number, and it's defined as this limit. And the limit exists indeed because we know exponential decay towards all the periodic orbits. So this remaining thing here now controls my energy on the complement of these, I guess. Let me write this as plus minus si, shifting the interval minus k. So that means I have a tail at minus infinity, I have a tail at plus infinity, and I have some large part in between. So maybe I'll get different color for that stuff again here. Some large interval in between, some tail here, some tail there. And the middle thing here, this is minus si plus this interval. And here, si plus that interval. All right, so that's my visual that I need to now make my arguments about something being small. Right, so my goal is still to write the UIs as x of something. So, you know, the shifts are pretty close to u minus and u plus, so I would claim that I can write just by these two convergences the ui in fact as the exponential at the preglued one, where I take this shift parameter as gluing parameter of some ci. Right, so that's why I chose the shift parameter, yeah, symmetric. So on these large sets, that's sort of fine just by the C infinity convergence. So I need to make sure that in between I can also write Ci that way. And that's where and then I want to make sure that I can make Ci as small as I wish. So I'd like to get the Ci at least less than that delta. And then we'll deal with the other condition next. So that's something where I felt the need to cheat.
Wait, I didn't. Sorry. I wasn't paying attention for a sec. Where I don't see how that implies that on the nice green patches that I could have this surjectivity here.
No, not surjectivity, I'm just saying so.
Like, no,
right,
like
so
right as the image of this.
So ui shifted is very close to u minus.
Yes.
Right, on this part. And that's essentially what I'm saying here. Right, so I'm saying that the difference between ui and u minus shifted is small, so the Ci is small. I mean, right, my visual, of course, is that ui somehow geometrically lies near the preglued curve. And I'm just trying to say that the error that I need to, between them is going to be small. So, yeah. So hopefully, sort of writing it out is going to make that even clearer. Right. So what I have here, well, right. I've already sort of made a couple of other steps here, right? So this preglued thing is, right, approximately equal to u minus of dot. Oh goodness, that's now plus si. And I'm just going to forget about the t parameter now. On some interval and u plus shifted elsewhere. And so I'm going to assume that my shift parameter is a lot bigger than the k parameter, right? And then si plus, oh goodness, this is going the wrong way. So then minus si plus this interval is going to be in that set where my pre-gluing is exactly equal to that, and the plus si shifted is going to be in the set where u plus is exactly the pre-glued one. Right. So that means on those sets I can get between ui and the pre-glued one by xc, right? That, so now this should be some w1p distance here. That's bounded by somehow the distance between the shifted ui and u minus. So if there's a shift here on the u minus and u plus, I'm just throwing that over onto the ui. So that's on those large intervals. The beauty on those large intervals is that because I have the C infinity log convergence, this here goes to 0 if, right, so my game is I have to fix k and then let I go to infinity. Because on every compact set I have this convergence. So, and now the idea is to fix k so that the whole error on all these other bits is going to be very small. So let's see, what are the other bits? So let me first look at this end here, so near minus infinity. There I've split things this way. Oops, no. Oh, I don't get to, okay, hold on. So let me just underline this. Right, so on that part, I ought to look at the distance between ui and u minus, or maybe 1. And right, because the cutoff, right, okay, yeah, right. So the pre-gluing is the shifted u minus all the way out here, the shifted u plus all the way out here. This interpolation in the pre-gluing happens on the middle bit. So I just need, again, to compare, right, between ui and the shifted u minus. And I can do that just by triangle inequality, comparing ui with the limit periodic orbit gamma minus, and then from gamma minus to the u minus. And the reason there's no shift here is that I can shift the gamma minus here somehow, the constant cylinder that always just keeps sitting at that periodic orbit. So I can shift that no matter how, that doesn't change. So I could have shifted both of these, but then I shifted back. So there's that term, and there's a very similar term from right here. That's I'm getting from comparing with u plus via the limit gamma plus. And let's see. So the claim is that I can make very small, so that this is less than some constant times my epsilon k. So why is that? Well, u plus is going to converge to gamma plus at near plus infinity, exponentially, and so I just take k large enough so that there's very little energy out at infinity, and that governs all estimates on that tail. Right, same thing for u minus at the minus infinity tail. And this part, these are the parts where I have very little energy, where my energy is controlled by this epsilon k. And so exponential decay gives me control of the W1P norms here in terms of the energy on those domains. So far so good? Okay. So then I have to worry about this middle bit, and that's the rest here. So that's the large middle bit of pretty large width, like 2k plus 2s. Oh no, 2s minus 2k. So this width here is 2si minus 2k. So that's a width that goes to infinity, but I again have very little energy on here. And so here I'm supposed to compare ui with the pre-gluing again, and the pre-gluing is either some cutoff of the u plus, some cutoff of the u minus. Oh, that is wrong here. X. Right, it's gamma here. Oops. Right, so we were writing on this domain, on the appropriate domain, we were writing u plus or minus as x gamma of eta plus and minus. And then we were using the beta to cut off that eta to the periodic orbit gamma where stuff breaks. So for a long time within that interval, the pre-gluing is in fact just gamma. So on that interval, this is exactly the distance that I need between ui and gamma. And then there's, some areas where the pre-gluing sort of gets interpolated to u minus and u plus. And that's where I need to then sort of make up for the error that I made here by looking at the difference between gamma and this cutoff stuff. And again, I was already generous. Instead of sort of taking this interval, I went all the way out to minus infinity or plus infinity. There's a shift that happened, here for the u plus and the u minus. And so again, by taking k large, there's little energy for the u plus and u minus, so these etas are exponentially small. So that controls these two terms, and then the final term, right? So the distance between ui and gamma, again, right? That's an interval where I have very, very little energy, and so then exponential decay again tells me that the holomorphic cylinder of very little energy has to be very close to a constant periodic orbit, and the closeness is governed by the energy. So I can get that small as well. So, and of course this is only ever true for, even here, right, this approximately equal here, I needed somehow the i's to be large enough. And that large enough depends on the k. So the game that I can now play here is to first make these two less than whatever, maybe the sum here, I make less than delta over 4 by taking k large. And then I can make the rest here also small. Because I've fixed k now, so now I'm taking I large enough to make this also less than delta over 4. For large enough i's. So overall, my norm of the CI's I can make less than delta over 2 for all large enough i's. I can now forget about the k. That was just sort of a crutch for the estimate. That was the hard part. That was the hard part that I'm doing explicitly. The other hard part I'm not going to do explicitly. But so, overall philosophy is, we have seen clearly log convergence on some bits, and on the rest we have little energy. So, questions about this? Otherwise, I'm going to delete it. So, what we got was Ci W1P less than delta over 2 for large I. So I could write zeta equal to xi, and then this would be satisfied, but I'm not in this complement of the kernel yet. So I would like to wiggle a little on my choices here. So right, if I have this expression here, I can shift ui a little bit. And I can still write it in the right-hand side form. Just my xi is going to have to change a little. And I can also change my gluing parameter a little. Yeah. And that's also going to force the xi to change a wee bit. So that's what we're doing here. So the important thing is that we have two parameters to play with. Oops. And that's not an epsilon, that's a different. So I'm playing with the gluing parameter with an r plus. And then I get a whole family of zetas that depend on r and epsilon.
It still doesn't really big, right?
Sorry?
If you, in the part where u changes quickly.
Right. I need to have
and
epsilon and r pretty small.
Or is it really big?
Right. I don't want that. So I want all my zeta r's to still be less than delta in norm, right? Because I want them to fit in here, right? But that's why I left myself delta over 2 space, right? And so I need r and epsilon small. But I do have this 2-parameter family of possible guys here. And now the claim is that playing with this 2-parameter family, I can run another implicit function theorem that gives me, I forgot my i's here, I guess, zeta. That gives me epsilon and r depending on the zeta i's, so depending on the I, so that this guy, oops, epsilon r I, epsilon I, is now in this right complement here. Okay, so this is the thing I need to still convince you of. And so here what we're going to do is we're going to write down an equation that solves for the whole thing. So first of all, the important thing to know is that, well, let's see. So the image of these dual operators are in fact, well, in some norm, and in some, well, and we haven't actually completely, discussed what they look like, but you could pick them so that their image is in fact an L2 perp of the kernel of the linearized operators. So this is the dual of the linearized operator at the preglued solution, right, of my d-bar operator. And now the important thing is that we do understand this kernel pretty well. So this kernel here is, well, approximately, this linearized operator is just a linearized operator for u minus on a large interval, and then shifted off the linearized operator for u plus. So this here is You could think of this as du minus somehow preglued. Well, with that, not write that number here. Preglued with the du plus. And so approximately this kernel is spanned by the two things that span these kernels. So and they're going to now depend on R. So where alpha minus is simply the S derivative of U minus, and alpha plus is simply the S derivative of U plus. Right, so that's in the kernel of the linearized operators of these guys. Well, that certainly is in the kernel because R shift is a symmetry. And then we assumed that we had index 0, well, sorry, Fredholm index 1, right? So we have isolated solutions. And that and they're cut out transversely, so the kernel in fact is just one-dimensional for these. And so then some piece of analysis says that the kernel of at the preglued one is then two-dimensional and is essentially spanned by these two. The only thing is that these depend on R a little because, of course, there's a shift here. Right? Something going on with. So that's the R dependence. All right. So with that, I can now actually say what it means to be in this image. Namely, it means to be perpendicular to these two guys. Right. So now I'm going to cheat. I want to write this as equality, and I have to hence write that as an approximate equality. So my alpha plus and minus will be the things that actually span this kernel, and they're now approximately equal to the ds. All right, so with that I can write my implicit function theorem for a function of two variables. Right. I would like to, well, I'm fixing the I, so I'm going to forget about that. Superscript, so I need to take the inner product between that C and the alpha minus and the inner product with alpha plus. So to check that there's an actual solution nearby, essentially I just need to check that the derivative of f at 0 is surjective. So for that purpose, I need to look at how how these x's, these are actually, I called them zetas here. Done. All right. Well, let me rename them into zetas. Right, so when I take the derivatives here, well, right, so two things happen. The R derivatives could hit the alpha minus and the alpha plus. But then these zetas here are very, very small. So pretty much nothing happens. So that's going to be a small term. So the zetas by themselves are approximately equal to 0. The epsilon derivative of zeta, they're always at epsilon equal to 0 now, is what? So I should write out what zeta is about someplace. And that comes, there's sort of this is the defining equation for the zeta. And let me just pretend that my symplectic manifold is Cn, and that the exponential map is simply addition. So then what this says here is that the zeta is the ui shifted, and then I have to subtract this preglued guy. But the preglued guy is essentially either the u minus shifted by s and r, or the u plus shifted by s and r. In different domains, right? And on the rest, well, u minus and u plus are very close to gamma. This is my sort of limiting orbit, and I'm sort of declaring that limiting orbit essentially 0 here when I write that. So if I look at that and try to take the epsilon derivative in it, well, the preglued thing here doesn't actually depend on epsilon. So I'm just getting the derivative of ui right? However, ui is we already know that ui is very close to the preglued thing. And now I just have to ask myself how the preglued thing itself changes, or what its s derivatives are. So, well, ui is u minus on some bit and u plus on some other bit. So this is going to be approximately equal to these two shifts of u minus and u plus. So that's about going to be alpha minus plus alpha plus. And that's it. Shift r equal to 0. Right, so u minus is approximately the pregluing of ui is approximately the pregluing of u minus and u plus. And so when I take its s derivative, it should be close to these s derivatives without the r here. So, and that happens to be the same thing as what is in this span here. That is our fortune here. And when I look at the r derivative, now I need to look at what happens here when I take the r derivative. So then the ui doesn't change with that r, just the gluing parameter here changes. And that does different things now. Changing that gluing parameter shifts u minus to the left and it shifts u plus to the right. So that's why I am going to pick up, what am I claiming here? Oh, right, and there's a minus sign in front of all of this. So that's what I'm saying. This is approximately equal to ds u minus shifted and then minus ds u plus. And that is about alpha minus alpha plus. And so the key really is this different sign. One is a plus, one is a minus. And that comes from epsilon being a shift that shifts everything in the same direction, and r being a change in the gluing parameter that shifts the two parts in different directions. So. And with that, I can calculate my linearized operator. Right, oh yeah, so the other thing the last thing that I should know is that these two things are concentrated, pretty close to. I think I have a sign error in everywhere, because the u minus should be shifted with a plus here, I think. And the u plus should have the minus. Right, because for very negative things I should have u minus, and for very positive things I should have u plus. Point being that this essentially the support of these two doesn't intersect, because they're shifted apart so much, so that the inner product between alpha minus and alpha plus is approximately 0. And so, if I do that, and I write out my R derivatives, so I think, what do I want? First column would be the R derivative, second column would be the epsilon derivative of f. I'm going to see a matrix like this. Key being this 1 minus sign here. And now I just need to know that neither alpha minus nor alpha plus is 0. So then this is two linear independent vectors, and so this is invertible. And that tells me that I can run an implicit function theorem to find a 0. And that is exactly the 0 that I need here to get into the right space. So, right, so that's the case of just the philosophy. So every approximate equal here now you have to replace by some argument that involves, C infinity log convergence and small energy on other parts. There are good reasons why people don't like to write these things out. Questions, confusions. You look unhappy.
No, I think it's so f of 0, 0 is certainly not 0 yet.
Right, but it's small.
It's small.
Because zeta is small. So you're right. Yeah, of course. So I should.
0 is then close enough in some sense.
Right. Yeah. So I should write. If I think back about the sort of Newton iteration theorem, there's a number of things I should check. Right. I should check that f at 0 is very small. I should check that f is C1 with uniformly bounded constants. Yes. All of these things. Yeah. Right. Yeah.
I'm not saying you should. I'm not asking you to check any of these things.
No. And I'm not going to. But yes. So and I should also say that f is C1. So all of these things together then. Let me run the implicit function theorem. Yeah, it's just that. So transversality is always sort of the main complication, and that's where some insight was needed here. There's also that's where the insight was needed, that you need to be able to play with two parameters that do slightly different things infinitesimally. So that was just to get, so you need to play with these two parameters and do all these estimates just to prove local surjectivity when you're image is actually one-dimensional. So now you can imagine what kind of hell breaks loose if your set of broken trajectories was actually positive dimension. So if we're not just trying to glue at an isolated broken trajectory, but we're trying to make sort of corner structure on the higher dimensional moduli spaces. Right? Because then you have to not only, right, so you have to, when you write this as rho of u minus u plus and the gluing parameter, you don't just have to find this shift and this gluing parameter, you actually have to find u minus and u plus from a whole family. And so, well, they live in some finite dimensional spaces that we've made transverse, hopefully, right? And so then you need to run an implicit function theorem over those two parameters and also varying u minus and u plus. So you need some good understanding that in your moduli space, the variation of the solutions, right? So you need some sort of local coordinate system there, in which the variation is very different from the variations that you get here from these derivatives. So, more stuff to check. And again, that's going to be fine when you're on some small bits of your moduli spaces. But you imagine if you now try to sort of let u minus and u plus vary in a larger set, then you'd need somehow all these estimates uniform. And that, I think, just gets dicey. So keep ourselves local with these things. Okay. Right. So that's just this little blue statement here, in this overall sort of geometric approach to, taking a possibly very singular moduli space and, giving it smooth structure. And so you wiggle with the J, and then you have to, glue the ends in to understand the compactified thing. So somehow the abstract regularization goes completely against this whole procedure of the geometric one, as it goes completely the other way around. It starts by just understanding what your compactified moduli space is. So first, that's the thing we need to first write out, and that's going to be this sort of space of holomorphic maps, modular automorphism, and on that level, on the sort of the topological level, there's a pre-gluing. Maybe right. So I shouldn't call this rho. I should call this. The topology comes from the pre-gluing broken ones. Because that is the only thing inside that's compact, right? So the idea is to write this compact thing as the zero set of some section. And the reason we need to do this is that the only tool that is inside, beyond somehow geometric magic, is this finite dimensional regularization theorem that we had, right? But that very clearly only worked when our zero set before perturbation was compact. So the whole idea of this abstract approach is to somehow write the entire compactified moduli space as a zero set of some section. Because otherwise there's no hope to have some general regularization theorem to deal with that. Right? And the reason why we have to do this is that regular J's don't always exist, and this rarely, so they exist. So, well, regular J's means that the d-bar operator is transverse. And the nice thing is when we get, d-bar operators themselves transverse, is that that preserves the symmetry. So that's the equivariant transversality, which we don't usually expect to exist. But in some cases we can actually find them, but this rarely has something to do with the geometry. Namely, when you run through the proof, you realize you need to understand some geometry of your curves, and essentially you'd like your curves to be somewhere injective in an appropriate sense. And so that is sometimes the case, and in some situations that I'll talk about in a little, that simply isn't the case. So when we can't do this, we need to, we can't hope for equivariant transversality, so the only thing we can then hope for is this, generalized abstract perturbation of sections theorem. So that's where you start with understanding what the space is that you need to now describe. And then, I started a while back to tell you that there are local Fredholm descriptions. So what I mean by that is now, so I'd like to sort of cover my compactified moduli space with some open sets that could be terribly singular. Jusa and I have started to call them footprints. They're the piece that sort of has geometric meaning of the charts. Namely, those are the actual holomorphic curves. But they come from Fredholm sections. Right, so I'm imagining some Banach manifold base, some bundle over it, some Fredholm section in it. And the relevance is that the zero set of that Fredholm section locally, is a part of my compactified moduli space. So I could phrase that more educated as saying there's a homeomorphism between that zero set and that footprint. So the footprint is just the zero set, and that somehow now sits inside this bigger thing and gets cut out by a Fredholm thing there. So this is the bit that we talked about just on the part of maps modular automorphisms by making the B sort of a local slice to the automorphism action. And then my Fredholm section was simply the d-bar operator restricted to that local slice. So the obvious question here is, how do you do that near the broken ones? But then the other question also is, well, now you have this cover, right? You want to think of somehow maybe describing M bar as something like a manifold, right? So then these are charts here. We do need to say how they fit together. After all, we're going to maybe like perturb these but then you have to perturb the nearby things also to somehow have, a meaningful theory. So I can write, hopefully, M bar actually as the disjoint union modulo some equivalence relation, and that equivalence relation is the transition information. So that should somehow come from actually sort of relating the different shards. This is a very abstract notation here. So this relation should come from something that we'll discuss at some point. But the beauty is that now I can, up to this quotient here, I can write this. This is a weird kind of section, but these are all the zero sets modded by some transition information. So it's a pretty abstract type of section here. But I want to think of it as a section, because then I can say what I mean by a regularization theorem.
Wait, in the end, you're gonna write. Oh wait, hold on. I'm just trying to immediately compare this because, like, in the previous approach, we just start by having it as some like zero set of some section, and then check a bunch of things.
Right, but there we had this whole thing, the whole big thing here, as zero set. Well, we had M twiddle as zero set.
Mm-hmm.
Right, and so we made that nice and smooth, and then quotiented, and then just did a gluing. Right. So here the problem is that we have only local slices to this automorphism action. So even for this bit, we can only cover it. It's not clear that you can find one local slice to all maps from spheres. Right, so, or even if you can find one local slice, you then have to compare it with other local slices. So to understand, we'll talk plenty about that. I want to give you sort of a rough overall idea here first. And indeed, it's very different from geometric regularization in that the Fredholm descriptions are very local, and that's why we need transition information.
But in the end, you're going to write it as a zero set of something global?
Right. Well, the problem here is, if I, let's say, what is my to-do list? Well, we understand this topology essentially. Let's say we even understand the local Fredholm descriptions on this nice non-nodal set. So first of all, I need local Fredholm descriptions near the broken stuff. I need to understand what my transition information is. I need to make sense of this. Right? In what sense is that a section of something? And then whatever that sense is, that's the sense in which I need to prove a regularization theorem.
So I assume this S is going to depend on all the SIs.
Yes, this S is given by all the SIs, right? Somehow modulo the transition. Let's dream for a moment, and let's just sort of dream of there not being broken trajectories and there being a global slice, so that my compactified moduli space is covered by a single footprint, which is the zero set of a single Fredholm section. So if that was so, then my regularization theorem was proven. Namely, it's simply that there's a set of nice perturbations for which the perturbed section is transverse to 0. And then the other thing I should make sure is that the perturbed zero set is still compact. Right. In infinite dimensions, that's not so obvious. And I would like it to be unique up to probability. And if we're in Hamiltonian Floer theory, then maybe I also want to know that the perturbed thing has the same boundary stratification that I expected. So I'd like the boundary of the compactified thing to be some fiber product of itself. Now, sort of very abstractly written. So, if that simply is just one Fredholm section, you can imagine proving this. However, in general, it's some other weird sense of a section, in some weird sense of a bundle, and you need, in that weird sense, you need to state and prove that theorem. And one part that there is not completely obvious is also then, well, what do you mean by transversality? And then whatever that meaning is should imply that this zero set is in fact has some kind of smooth structure, or at least C0 manifold structure. So that's a wish list or to-do list. We wanted to have a nice machinery that counts holomorphic curves.
So this is you and McDuff's idea?
No, this is general idea. This is what was out there. This is me general. I mean, this is sort of my, I guess. Nobody ever wrote things down in that form, nor did Duza and I. But I think this is the general summary of all approaches out there that don't just wiggle J. These ideas go into them. It's just, you could now. So if somebody tells you about one of these approaches, what you can ask them, the two things that you should ask them is, well, what is this section that you speak of, and then what is the regularization theorem? So, Kuranishi structures in some sense are this. Polyfolds in some sense are, writing things as a zero set. So is, all the other virtual moduli cycle techniques all write something as a zero set, and then prove something about that section.
So there's probably no reference.
No,
Okay.
this is
it.
This is it. Yes, I'm making the reference. Right? And jeez. Right. Since I'm making the reference, I am very slow. Right. So I'm not going to actually get to the non-transverse gluing. But I'm also not going to say anything. So the why I'll start with next week. So examples of when we can't expect regular J. So since we have this sort of nice Fredholm description here, I want to somehow say what the one core of an idea is that one could do now. Because that will come over and over again. Right? So let's say we have a Fredholm section that sort of locally describes our compactified moduli space, and sigma fails to be transverse to zero. Then what do? So first of all, there's something that you could call obstruction bundle, which is the union of the co-kernels. So EB is the fiber over B mod the image of the linearized section. And I might want to look at that over the zero set. So that's then, well, it is a bunch of finite dimensional vector spaces over this possibly pretty singular zero set. There are cases where my zero set R is actually a smooth manifold. It's just too high dimensional because the co-kernel is always, maybe two-dimensional. So, and then there's some hope that I get a nice bundle here. And so I could, try doing something with that bundle. In general, that's just a whole bunch of vector spaces over some singular set with no good structure. But the core idea is that one can stabilize these things. So one can find a finite rank subbundle over, again, then some neighborhood now of the zero set. So finite rank, so that that covers all the co-kernels. But I didn't write direct sum here, because sometimes there might, the dimensions might jump. But if I take this big enough, the hope is in sum. At least if I make maybe the domain here even smaller, in the neighborhood of a single point, I can get this. That's a sort of surjectivity statement, and surjectivity is open, so one can do that. And the cool thing is that then one can then look at the set of points in B for which sigma of B isn't quite zero, but is in E. That then will actually be transversely cut out. So that will be a smooth manifold. And I can now think of E as a bundle over this. This is now a finite rank bundle. And there's a section, namely simply taking sigma. So this is what one would call a finite dimensional reduction. So I should probably call this B sub E, and this is the section restricted to that. Maybe call that S. And so what I have here is some bundle over some base, all finite dimensional, and my homeomorphism is now from this zero set of the finite dimensional thing into M bar. Local. And so all that worked was to go just from a Fredholm section to a very special Fredholm section, namely one that's in finite dimensional bundles. So that's then the world of Kuranishi structures. And there's other sort of approaches that kind of stop after the stabilization. And I'm going to need the stabilization idea to then talk about what you do when you try to glue in non-transverse cases. So we'll do this again more precisely next week, and then very imprecisely mumble what kind of gluing one does in that context.